Hello and welcome everybody to another episode of نوير يدرس. Today we'll be going through thermodynamics, but we already covered thermodynamics in chemistry. How about we cover it in physics? So we're gonna speaking about thermodynamics in a physics aspect. So just to recover our information, zeroth law of the thermodynamics states that if two systems are in thermal equilibrium with a third system, these two systems are in thermal equilibrium with each other. So A equal B and B equals C. So C is equal A. So everything is in thermal equilibrium with each other. And remember, third law of thermodynamics is absolute zero, which happens at negative 273 Celsius or 0 Kelvin. So we have a new concept here, which is thermal expansion. Thermal expansion is when there is a general increase in volume as temperature increases, and when temperature decreases, there is a decrease in length. So let's say you heat something up, it expands, but then you cool something, it decreases its length. And then for this, we have this equation delta L, the length, is equal to the coefficient of temperature, which usually I think is given on test, times length times d delta t. So that's like final minus initial. So we have an example here. So we have an aluminum bar at 1.25 meters, which is the length, at 20 Celsius. So that's the initial. And then the coefficient for the linear expansion, which is this one, is 2.5 times 10 to the negative 26, times 10 to the negative 6. If temperature is increased to 25 Celsius, what will the length change be and what is the new length? So like I said, it's the coefficient times the length, and then here is 75 minus 25. 75 is the final minus the initial, so that's the new length um, that we have here, so 0.00172 meters, and then it's added to the original length to give us 1.2517 meters. So that's how you calculate thermal expansion. Next, we have the three types of systems. We have the isolated system. Isolated system here is where like energy nor matter can exchange with the system. So for instance, we have a thermal flask containing hot coffee. Doesn't allow anything out, doesn't allow anything in, and the internal energy is equal to 0. Next, we have the closed system. With the closed system, um, you're able to exchange energies but not matter with the surroundings, and it allows energy to leave. So, for instance, you have a steam engine, and in a steam engine, you have the water and fuel are within the engine. That's the matter. But the engine converts the thermal energy of the steam into mechanical work. And then lastly, we have an open system. With the open system, it exchanges energy and matter with the surrounding. For instance, you have a plant growing in a garden, it exchanges nutrients and exchanges energy, and it's just in an open surrounding. Next, we have thermodynamic properties. What are the thermodynamic properties? We already covered them previously in the chemistry video, but here the thermodynamic properties are temperature, volume, pressure, entropy, and enthalpy. And then we have the change in internal energy. It's when heat is transferred to a system, it's the amount of energy transferred to a system. So it's like heat transferred to a system. So like basically the amount of energy transferred to and from a system. So delta U, which is the delta internal energy, equal heat minus work. And then if the internal energy decreases, heat is lost from the system or work done on. But if internal energy increases, heat is gained and um, work is done by. So here we have a table I created where it shows that whether it's going to be a positive value or negative value and why. So with the internal temperature, with the internal energy, when you increase temperature, there's a positive value, but when you decrease the temperature, there's a negative value. And then heat, when heat flows into the system, it's a positive value. The system gains heat. When the heat flows out of the system, it's a negative value. The system loses heat. Work done by a system such as expansion, so the system expands, an external factor worked on the system, and then a negative value no, sorry, work done by the system, such as expand the system itself helps expand, and work done on the system, external factors, it compresses. Sorry for the earlier confusion. Next, we have the heat transfer between objects. So heat transfers between objects through multiple ways: conduction, convection, and radiation. Conduction is the direct transfer of heat through physical contact, and gases are really bad conductors because they're far away from each other. Transferring heat using gases is really, really bad. Next, you have convention. So it's the transfer of heat by physical motion of fluids, so that's liquids and gases. So if fluids have high temperature, it will transfer energy to other materials. So a convention works best with liquids and fluids. So, and then lastly we have radiation, which is the energy transferred by electromagnetic waves. And just this type of heat transfer, it can transfer energy in a vacuum. Next we have the heat, what is it called? The heat formula, which is MCAT or MC delta T, which is M times the specific heat transfer times the final minus initial. And then you can also calculate it through another way, is M times L, and L is the heat of transformation. Next we have the transformation heats of transformation or transformation energy. So from a liquid to a solid, it's called solidification, and from solid to a liquid, it's heat of fusion, and then from a liquid to gas, it's vaporization. So going the more I would say energy needed to be put in. So for instance, going from a solid to a liquid, so you need to put energy to melt in the solid, right? Heat of fusion, and then you need to put in more energy to vaporize the liquid to become a gas. When the internal energy is zero, it's isothermal, and heat is equal to work and temperature is constant. But what if the heat is equal to zero? It's adiabatic. So adiabatic process is the process of no exchange of energy between the system and its environment in the form of heat. So there's no heat exchange. And then when work is zero, it's isovolumetric, and the internal energy, delta internal energy is equal to heat volume is constant. So when work is zero, volume is constant. When heat is zero, no heat exchange. And then when internal energy is zero, temperature is constant. Alright, thank you so much for tuning in. Let me know if you have any questions, and make sure to check out our other videos.